As you're no doubt aware, you can't get something for nothing. Voltage and current are related properties via Ohm's law. Perhaps you've heard of it. Power, another important electrical property, is the product of voltage and current, and this is perhaps the best perspective to approach this relationship from. If we assume a given transformer to be ideal, meaning it is 100% efficient, we can assume all power input to the transformer is transferred to the output with no losses in the transformation. In summary, power in equals power out. I'll come back to explain losses for non-ideal transformers in a later lecture. For now, let's just go with it. Given the function of a transformer is to step up or step down voltage, a given power is a product of voltage and current. If voltage at the secondary input is higher than the primary input, current drawn from the primary must proportionally increase to achieve the required power transfer. Conversely, if voltage at the secondary output is lower than the primary input voltage, current drawn by the primary needn't be as large to transfer the required amount of power. Given voltage and current are related properties, as are voltage and turns ratio, one could express this more succinctly as the number of turns in the secondary over the number of turns in the primary equals the input current through the primary over the output current through the secondary. Ns over Np equals Ip over Is. This makes perfect sense. Voltage has a directly proportional relationship with turns ratio, whereas current has an inversely proportional relationship with turns ratio. Importantly, the current drawn, either from the primary or secondary, will always be reflective of Ohm's law and the load demanding current. Consider an application in which a 5-to-1 step-down transformer is being used to power, let's say, a desk lamp that necessitates 24 volts AC to operate, where the bulb is modeled as a 50 ohm resistor. As we previously demonstrated, this would necessitate a 120 volt AC source in the primary to provide the input voltage necessary for the 5-to-1 step-down transformer to produce the necessary 24 volt AC output. Through simple Ohm's law manipulation, we'd expect the current in the secondary to be 24 over 50, or roughly 480 milliamps. Apparent power is therefore roughly 11.52 volt amperes, all of which is being directed towards 11.5 watts of real power, and none of it towards a reactive interchange, given the bulb is modeled as a purely resistive load. If this ideal transformer was truly 100% efficient, we can say power in equals power out. Given our power output at the primary is 11.5 volt amperes, we could say our power input at the primary to be also 11.5 volt amperes. We can use this power figure to solve for current in the primary. Given apparent power is the complex conjugate of the voltage times the current, we can substitute our given values and solve for the current. Doing so yields a current of only 96 milliamperes drawn from the source by the primary winding. This makes perfect sense. For this step-down transformer, the primary provides high voltage, low current input, where the input power, the product of voltage and current, is 11.5 volt amperes. In contrast, the secondary provides low voltage, high current output, where the output power again is a product of voltage and current, is also 11.5 volt amperes. Additionally, using our previously demonstrated inverse relationship between turns ratio and current, we can also solve for current directly without having to solve for a power intermediary. As we discussed, the number of turns on the secondary over the number of turns on the primary equals the input current through the primary over the output current through the secondary. Ns over Np equals Ip over Is. Given we know the turns ratio to be 5-to-1, and the current drawn by the 50 ohm load from the 24 volt secondary output to be 480 milliamperes, we can substitute in these given values and solve for primary current. Doing so again yields a current drawn by the primary winding from the source to be 96 milliamperes. In summary, given output voltage is 1/5 of input voltage, output current will be 5 times input current. Put another way, given input voltage is 5 times output voltage, input current will be 1/5 times output current. Either way you look at it, there is a directly proportional relationship between turns ratio and voltage, and an inversely proportional relationship with turns ratio and current. In keeping with this observation, see if you can solve for both the secondary and primary current given the same 5-to-1 step-down transformer powered by 120 volts AC input when the bulb modeled as a 50 ohm resistive load is swapped out for one with only 20 ohms of resistance. This might be a high power setting where the desk lamp is being asked to supply more light. Speaking of power, additionally, see if you can solve for power input to and output by the transformer, assuming 100% efficiency. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Ohm's law shows that the 20 ohm resistive load now draws 1.2 amps from the 24 volt secondary output. Given current has an inversely proportional relationship with turns ratio, we find that the primary winding would now draw 240 milliamperes from the 120 volt source. Given these voltage and current values, the apparent power output by the secondary winding would be 28.8 volt amperes, all of which is being directed towards 28.8 watts of real power, and none of it towards a reactive interchange. Similarly, assuming 100% efficiency, the apparent power input to the primary winding would be 28.8 volt amperes, all of which is being directed towards 28.8 watts of real power, and none of it towards a reactive interchange. Before moving on, consider the impedance seen by the source through the transformer for both occasions. First with a 50 ohm resistive load, and again with a 20 ohm resistive load. The 120 volt source doesn't know it's being asked to power a 5-to-1 transformer, which in turn is powering these two loads. All the source knows is in the first scenario, it's supplying 96 milliamperes of current, and the second 240 milliamperes of current. My question to you is this: what is the impedance seen by the source through the transformer for both occasions? This phenomenon is known as reflected impedance and has everything to do with the degree of magnetic coupling between the primary and secondary coils. Yes, current flowing in the primary magnetically couples the secondary to the primary. However, current flowing in the secondary also magnetically couples the primary to the secondary. Despite there being no direct physical nor electrical connection between the source and the load, the source still sees an impedance, and current drawn from it will behave according to Ohm's law. In the first scenario, when the bulb is modeled as a 50 ohm resistance, we demonstrated that the source supplies 96 milliamperes of current. Using Ohm's law, this demonstrates that the source in effect sees 1,250 ohms of impedance. In the second scenario, when the load is modeled as a decreased 20 ohm resistance and is drawing more current from the secondary, we demonstrated that the source also supplies an increased amount of 240 milliamperes of current. Using Ohm's law, demonstrate that the source in effect sees 500 ohms of impedance. Pause to consider how the reflected impedance seen by the source, 1250 for the first scenario and 500 ohms for the second scenario, relates to the actual impedance on the secondary, 50 ohms for the first scenario and 20 ohms for the second scenario. You should note that for both occasions, the reflected impedance seen by the source is 25 times that actually on the secondary. 25 times is in fact our turns ratio of 5/1 squared. In addition to the previously discussed relationships for voltage and current and turns ratio, we can also state that the reflected impedance seen by the source is the turns ratio squared times the load impedance. Note, in ideal transformer scenarios, the reflected impedance changes the magnitude of the impedance seen by the source, not its angle. The source in this application sees solely a resistive element with a phase shift of 0 degrees. Let's try a complete example problem illustrating the wonderful utility of turns ratio. Consider a 1.73-to-1 step-down control transformer powered by 208 volts, providing current to a purely resistive load of 1.6 kiloohms. I'm asking you to solve for the secondary voltage, the secondary current, and the power output by the secondary winding. Additionally, solve for the primary current, the primary power, and the reflected impedance seen by the source. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Given our turns ratio is 1.7321 and voltage is directly proportional to turns ratio, primary over secondary, our given values suggest that the secondary output of the transformer will be roughly 120 volts. When 120 volts is applied to a 1.6 kiloohm resistor, Ohm's law demonstrates the current through the load will be roughly 75 milliamperes. The power equations demonstrate that this load will experience 9 volt amperes of apparent power, all of which is being directed towards 9 watts of real power, and none of it towards a reactive interchange, given this is a purely resistive element. Power input would also be 9 volt amperes, all of it being real power. Using either of these power figures, or the inversely proportional relationship of turns ratio and current, we find that the current in the primary will be roughly 43.4 milliamperes. Finally, either the turns ratio squared times load impedance or Ohm's law demonstrate that the source is seeing a reflected impedance of roughly 4.8 kiloohms at an angle of 0 degrees. Additionally, one could have solved for reflected impedance seen by the primary first, and then use this figure to solve for current in the primary. Regardless of the technique or order applied, you should have come up with the same results. That's the point. There's more than one way of getting the correct results, and alternate methods make a great way of checking your work. Let's try another illustrated example, this time featuring a step-up transformer meant to supply 220 volts to a motor modeled as an impedance of 260 ohms at an angle of 32 degrees using 120 volt input. Given this input and the desired output voltage, see if you can determine the required turns ratio, the current in the secondary output, and the power output by the secondary. Additionally, solve for the primary input current, the primary power input, and the reflected impedance seen by this source. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. To step up 120 volt input to 220 volt output would necessitate a transformer with a turns ratio of approximately 1 to 1.83. When 220 volts is applied to our motor winding modeled as an impedance of roughly 260 ohms at an angle of 32 degrees, Ohm's law suggests that the current through the secondary winding will be roughly 846 milliamperes at an angle of negative 32 degrees. The power equations show that this load will experience 186.2 volt amperes of apparent power, 157.9 watts of which is being directed towards real power, and positive 98.6 bars being directed towards a reactive interchange. Power input would also be 157.9 watts and 98.6 bars. Using either of these power figures, or the inversely proportional relationship of turns ratio and current, we find current drawn by the primary will be roughly 1.6 amps at an angle of negative 32 degrees. As can be expected, current drawn by the low voltage primary would be larger than the current drawn by the high voltage secondary to transfer the required amount of power. Finally, either the turns ratio of 1 over 1.83 squared times load impedance or Ohm's law demonstrates that the source is seeing a reflected impedance of roughly 77.6 ohms at an angle of positive 32 degrees. Alright, I do believe I've covered everything I intended to in this particular lecture. We'll examine transformer efficiency and voltage regulation, as well as transformer winding polarity and different types of transformer connections in later lectures. Before closing out this particular lecture, however, let me answer this very pertinent question. Why transform at all? The simple answer might be because different devices necessitate different voltage levels. Consider a transformer primary supplied by incoming 600 volts. However, it contains not one, but several different secondary windings. One with a 1.25 to 1 turns ratio, another with a 2.5 to 1 turns ratio, and yet another with a 5 to 1 turns ratio. Given turns ratio is directly proportional to voltage, it can be demonstrated that the first secondary winding will have an output voltage of 480 volts, the second secondary winding will have an output voltage of 240 volts, and finally the third secondary winding will have an output voltage of 120 volts. This single transformer with multiple secondary windings, each with a different turns ratio with respect to the primary input coil, thus serves as a centralized means of distributing and isolating 3 different voltage surface levels for 3 different intended purposes. For example, the 480 volt output could serve as some hoist, the 240 volt output could serve as some heater, and finally the 120 volt output could serve as some shop lights, a couple outlets, and maybe power a computer. In a larger sense, transformers are absolutely essential to getting power from where it's generated to where it's being used. Step-up transformers make it possible to transmit massive amounts of power over long distances with extremely small losses. Allow me to demonstrate. For this example, let's assume voltage and current are perfectly in phase with one another, and as such, all of apparent power will be directed towards real power and none of it towards a reactive interchange. Consider a 500 kilowatt generator that operates at 690 volts. A simple algebraic rearrangement of the apparent power formula suggests that this generator is producing approximately 724.6 amps, an astronomical amount of current. Now, consider this generator being asked to supply power to a city 200 plus miles away with a long transmission line made of thick, highly conductive, extremely expensive material is modeled as a 0.5 ohm resistor. You'd think 0.5 ohms of resistance might not be a deal breaker, but recall that power is proportional to current squared times resistance. With such an astronomical amount of current being sent through this line, we might expect there to be a large power loss in the line alone. Given the generator is forcing 724.6 amps through the 0.5 ohm transmission line, the power equation shows that the line alone is dissipating roughly 262.5 kilowatts of the available 500 kilowatts, leaving only 237.5 kilowatts, less than half the original 500 kilowatts, available for use at the distant city. Ohm's law additionally suggests that there will be a 362.3 voltage drop across the line, leaving only 690 minus 362.3, or 327.7 volts at the distant city. This transmission scheme without transformation is essentially wasting more than half the power generated just getting it to the point of use. Rather than serving to transmit power, we've effectively turned the transmission line into a 200-mile-long toaster. This will not work, and another means of transmitting power over long distances must be employed. A far better solution to this conundrum is to use two transformers, one at each end of the long transmission line. The first being the transmission transformer at the point of generation, which steps voltage up from 690 volts to 34.5 kilovolts, and the second being a distribution transformer at the point of use, which steps transmission voltage down to an appropriate level for a delivery to industrial and residential users. We'll concern ourselves largely with the transmission transformer for this illustrated example. Given the 1 to 50 step-up transmission transformer is increasing voltage 50 times, current will be 50 times lower. That's the point of a step-up transformer. By stepping up voltage, we can step down current, yet still transmit the same amount of power. Given the 500 kilowatt generator must supply 724.6 amps to the input of the transformer to deliver the required 500 kilowatts of power at 690 volts. It can be demonstrated the output current of the secondary winding will only be 14.5 amps. Given only 14.5 amps of current is now traveling through the 0.5 ohm transmission line, the power equation shows that the line is now dissipating only roughly 105 watts of the available 500 kilowatts, leaving a substantially larger portion of 499.9 kilowatts, essentially all that was generated, available for use at the distant city. Ohm's law additionally suggests that there will be only a 7.2 volt drop across the line, leaving 34,492.8 volts at the distribution transformer in the distant city. In fact, the power losses and voltage drop across the line are so small in comparison, they're almost negligible. By stepping up voltage and proportionally stepping down current, we transfer a significantly larger portion of the original power generated by the remote facility to the city with less line losses. This, above all the other numerous benefits and applications, is why the transformer is such an integral part of modern society. For a device with no moving parts, I find the utility of the transformer absolutely fascinating. Alright, that's about it for now. In conclusion, this lecture examined the transformer, an electrical device used to step up or step down AC voltage. We learned the turns ratio, the number of turns on the primary, over the number of turns on the secondary, is directly proportional to voltage and inversely proportional to current. Additionally, we learned that a source supplying current to an ideal transformer sees a reflected impedance equal to the load impedance times the turns ratio squared. We assumed ideal transformers are 100% efficient, and operating under this somewhat dubious assumption, we can say power in equals power out. Finally, we learned that transformers are an essential component of the modern electrical grid and make it possible to transmit electrical power over vast distances with minimal losses. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.